We are surrounded by chemicals, from salt to cellulose to paracetamol, ibuprofen, and even the world's most lethal toxin, Botox. We are a bunch of chemicals, and we interact with many more in our environment. So it pays to know what they look like and how they will interact with each other. However, we can't see individual chemicals. Or can we? I'm Almost a Doctor. Welcome. In today's video, we're going to look at a few techniques that allow us to see chemicals. I mean, if you look it up, a crowd favourite is ethanol. Looks like this. Or you might look up a sugar, say glucose, and you'll get this. But how do we know these are correct? You might think that we can determine what all these chemicals look like by using what is essentially a fancy Lego kit and just putting all the atoms together and seeing what it looks like. Whilst this might work for ethanol, it's not going to work for something more complicated like tetrodotoxin. There's just too many ways you can put all these atoms together to know exactly what we've got. So where to start? Well, before we look at entire molecules, let's go back to the beginning with the birth of the field of spectroscopy and look at some elements. Spectroscopy is the study of the interaction between light and matter. Whilst you'd never be able to build a light microscope powerful enough to see individual atoms, no matter how large you made it, you can still see what happens when photons interact with individual molecules or elements. You can see the smoke, but you can't see the fire. Spectroscopy harks back to the days of Newton. Whilst this image of splitting light with a prism is well known, being able to separate wavelengths was our first step to understanding the world of the elements that surround us. Individual atoms can absorb and emit photons. If we hit an atom with a photon, then we can transfer the energy into its electrons, and the molecule enters what's known as the excited state. Likewise, an excited molecule can relax and give off a photon. For this to work, however, we need to match the energy of our photon to the energy differences in the electronic levels of our atom. This means that since every atom has different electronic levels, we need photons of different energies. Since photons of different energies have different wavelengths or colours, then by observing what unique colours are either absorbed or emitted in a given sample, we can figure out what elements are present. It's actually surprisingly easy to do. Check this out. Now that we've had a look at how to identify elements that are in a sample, we need to go beyond and have a look at whole molecules. Whilst molecules can still absorb and emit visible light, we still can't determine much about their structure using this technique. So far though, we've only looked at the visible part of the electromagnetic spectrum. Whilst the electromagnetic spectrum is technically endless, normally wavelengths range from the high energy gamma of about 1 angstrom all the way up to the extremely low energy 1 kilometer radio waves. However, if I was to stretch this scale out between here and the moon, then the portion representative of the visible part of the spectra would only be about 11.5 centimeters. So about this much, which is, as you can see, not a lot. So it's not surprising that over the years we've found other ways to utilize different portions of the electromagnetic spectrum to see even more about molecules. Many of you have probably had an X-ray at some point in your life. But did you know that you can actually take an X-ray of a chemical? And it kind of looks like this. And in fact, this here is table salt, or sodium chloride. And it won father and son team, William Henry and William Lawrence Bragg, their 1915 Nobel Prize. But what's going on? How does this equal this? Well, it all has to do with the fact that X-ray photons are about 1,000 times smaller than visible light photons, and that matter is mainly empty space, or at least the distance between nuclei is significantly bigger than the diameter of the nuclei themselves. If we fire X-rays through a sample, then the photons can sometimes interact with the nuclei. And when they do, they'll either be deflected or diffracted. And based on the spacings between the nuclei and their arrangement will depend on exactly how and where these photons are deflected to. What we can do then is start with a pattern like this and do a bit of maths and work backwards and determine what structure must have given that pattern. In order to utilize this technique, however, you do need a regular repeating structure. But when you get that, this is an incredibly powerful tool and has led to some of our most famous discoveries, including Rosalind Franklin's experiments that allowed Watson and Crick to determine the structure of DNA, the 1964 Nobel Prize to Dorothy Hodgkin, who determined the structure of vitamin B12, and has even led us to understand what HIV looks like, which allowed for the development of certain drugs that have saved countless lives. So we're done, right? Well, not quite. There are still chemicals that we can't yet determine. So for that, we're going to need a big magnet. And instead, we're going to switch to the other end of the electromagnetic spectrum and look at some radio waves. Probably one of the most powerful techniques in modern chemistry for determining what chemicals look like is nuclear magnetic resonance. The nuclear refers to the nucleus of an atom. In NMR, that's nuclei with an odd atomic mass, the most common being these two, protons and carbon-13. The magnetic resonance is a bit trickier, so I might leave the full explanation for another day. But essentially it refers to how the nuclei responds to an external magnetic field. Nuclear resonance was first noticed in 1946, and in 1950 it was noticed that each nuclei responded slightly differently depending on what atoms and chemical bonds were around it in the molecule. In fact, these differences, although sometimes subtle, are enough that you can tell exactly what is next to what. Since the first machine was patented almost 70 years ago, NMR has come a long way. In fact, modern machines often utilize superconducting magnets cooled with liquid helium. The magnetic field is so strong that if you get close to it with your wallet, then it will wipe your credit cards. However, these machines are so sensitive that if you change even one chemical bond in a large molecule, you can tell the difference. These techniques are by no means exhaustive. Others include neutron scattering, infrared and mass spectroscopy, just to name a few. But hopefully I've been able to give you a brief insight into the world of looking at chemicals through spectroscopy. If you've liked today's video, don't forget the usual like and subscribe below. And if you have any suggestions for topics you want to see, check out my previous video where I'll take the 2 most liked comments and turn them into videos no matter what they are. And remember, I'm almost a doctor, and until next time, be like a proton, stay positive.